before that, I wanted to discuss a little bit more about some of the basics of how things work, especially in the context of quantum sensing. So that's really where my research is kind of is more focused, is quantum sensing. But that's of course very closely related to quantum computing in the sense that we're working with qubits and entangled bits. So I will. But I think what I really think is very exciting is the use of qubits as quantum sensing. And I suspect that you quantum computing people, you probably have you may not have heard about quantum sensing, and you probably heard about different types of quantum qubits, but one particular qubit that's very it's very interesting from a fundamental physics point of view, and also for possible applications as a quantum sensor is called the NV center, or nitrogen vacancy center. It's a kind of color center that is in diamond, and so I'll explain a little bit of what that means. Okay, so diamond, you may know, is a lattice of carbon atoms, and every carbon is bonded with 4 nearest neighbors, as you can see in this kind of lattice here, and it's a very well understood material that is the lattice structure is really well known, and the electronic properties. It's actually can you see okay? Is the screen okay? So this is actually an insulator. Diamond is transparent and it does not conduct electricity. But as most crystals, there are naturally occurring defects that occur in it. And there is a particular kind of defect called the nitrogen vacancy center, and where there is instead of a carbon atom, you have a nitrogen, and right next to it is an empty site, so a vacancy. And this object forms a localized electronic state, and on the right-hand side is actually a picture of the wave function of the electronic wave function of the NV center. So these little balls here are carbon atoms, and the wave function is spread out over this kind of yellow blob. So the yellow blob tells you the probability of where you would find an electron in the lattice. So it's localized around this NV center, and it has some very special properties. On the left, you can see just a picture from my lab where we're shining a green laser onto a diamond with NV centers, and you can see it looks kind of reddish here, and that reddish color is coming from these NV centers. So NV center is one example of a defect state in a crystal, and these have been studied for decades. They're known as color centers because they're responsible for what gives crystals different colors. So, for example, well, okay, so I just want to explain a little bit about the quantum mechanics of this. This is we can think of this state as kind of like an artificial atom. It's essentially it has bound states of electrons that live in a well-controlled position in space, and we can take advantage of those for either quantum computing or for sensing. And in a sense, we could imagine coupling a whole set of NV centers together and performing quantum computing algorithms or something. And people have actually done this sort of thing. But to sort of give a little more background, I mean, yeah, sorry, this may be a little introductory, but I think it's useful to cover it. So, imagine that if you were to take like a classical particle and you put it in a box and it's bouncing around in there, you would kind of classically, you would expect you could find any energy for that ball to be inside that box. And it would be more or less uniform probability to find it anywhere inside the box if you just randomly threw a ball in there. So that's kind of a model system for how an atom or an NV center is. There's a region of space where the electron could be, and but when you think about it from a quantum mechanics point of view, things change. In fact, from a quantum mechanical point of view, there's only certain energies allowed. This is the idea of quantization, and so there's only specific energies allowed. And you know, for a particle in a one-dimensional box, you may have seen this problem before in maybe one of your classes, that there's only certain energies that are allowed for that particle to actually be inside that box. And it's related to trying to fit in a wave in the size of that box of length L, say, for example. So you have to have an integer number of half wavelengths for that particle to be inside the box, and anything in between is not allowed. And so, you know, this really gets into this picture of the sort of wave particle duality of quantum mechanics that is very non-intuitive. So, you know, it's funny to think about it, and you know, it's the sort of thing that if you can't sleep at night because it's bothering you to try to resolve this, that's probably a good thing. You know, if you don't understand it, many smart people have really been puzzled over this. However, we know it's a very accurate representation, to a high degree of precision. So okay, so this is like just a nice one-dimensional model of a box. You know, in many cases, this can be generalized to 3 dimensions and so on, and it can be, this is actually really relevant. So the really key here is that only light, let's say that you have you shine light onto this problem, onto this particle, there can be a transition only when the energy matches the energy difference between 2 energy levels. So there's very discrete values of energy that can give rise to transitions. And of course, that's very discrete levels of light with specific wavelengths. So only specific wavelengths can cause transitions. So yeah, I don't know if you've ever seen, by the way, let me just stop and ask, please, if you have any questions, please interrupt me, okay? It's kind of hard to talk on Zoom without actually seeing your audience because you sort of talk into this vacuum. So I'm really happy if you ask any questions, okay? So when you may have seen pictures like there's this kind of nice website called Web Elements. It's a periodic table website, and you can, if you click on part of it on the periodic table, you can see a particular element, and it will show you the spectrum of that element. So there shows you like a black band, and there's little color lines, and that's the kind of, those are the transitions frequencies that are allowed for that particular atom. And those are really the fingerprint based on these energy levels spacing for that atom. And so that's kind of nice. If and you know, that when that was first observed, people who developed quantum mechanics, this was really important for them to understand the whole idea of quantization of energy levels. So you know, instead of just this nice little one-dimensional box problem, you know, this really happens in real life, and it's probably maybe happening right now in your monitor of your computer or in your TV. So they talk about these things called QLEDs or something like that, and this is based on. So imagine instead of a cubic box, you have like a spherical shell. So you have this region of space between an inner diameter and an outer diameter of a sphere where the electrons can live. And so you might create such a thing by making a tiny piece of material and surrounding it by metal. And the electrons can live in the metal, but they can't live in the insulating center or the outside. So it's kind of like a bounding box for that electron. And so only the most important parameter that decides the energy level spacing is the diameter here, the radius, or the distance between the inner diameter and the outer diameter. So this is exactly what happens in quantum dots. So you can engineer these things in the laboratory using like nano dots, nano size pieces of metal. And by tuning the size, you can change the wavelength of the light that they will absorb or fluoresce. And you see this really beautiful control over the color of the light based on the size, right? The color is corresponding to the wavelength. So this is a really, this kind of physics is really particle in a box kind of thing where you have quantization of energy levels. So, and of course, this is what people can control very nicely with TVs now. Turns out the same thing, the same thing is true for a color center in a crystal. So this is why certain gemstones have particular colors, right? So up here is this is the crystal structure of aluminum oxide. So this is actually kind of this boring white powder. Usually, aluminum oxide is kind of it's not really interesting. But if you put in a little bit of an impurity in it, chromium impurities, you get ruby, which of course is this beautiful pink color. And there are small number of defects in this structure which have ruby, and they form a little bound state with quantized energy levels, and those quantized energy levels correspond with this beautiful pink color. That's why they're called color centers, and they give this color here. Instead of ruby, if you put in titanium impurities, slightly different structure, but it's still this, it's the same crystal structure, it's just a different color defect, titanium defect, it becomes blue, and it's a sapphire. It's the same crystal, it's just a slightly different defect. So it's the defects that are really giving these things colors, right? So, I mean, I gave this class previously to a group of people who were really interested in gemstones. So I have several other examples, right? So here's another crystal structure for beryl. It's beryllium, aluminum, silicon, and oxygen. And there's several different varieties of gemstones based on this crystal structure with just different kinds of impurities. If you have chromium impurities, you get green emeralds. If it's manganese, you get kind of brownish color, like right here. And if you put iron impurities, it gets this beautiful turquoise, bluish sea color, aquamarine. So, you can go and buy these gemstones. They occur naturally in different parts of the world. And it just happens to be what's the locally, what is the kind of impurities that grow into those crystals. Yeah, here's another example, yet another one. It's called elbaite. And this one's kind of impressive because there's a whole range of different colors that you can go from reddish to blue and green. Again, this is all the same physics of color centers, where you put these defects in, and the defect essentially forms like an atom where you have a localized set of electrons with different energy level structures, and it's the energy level structure that gives rise to the color. And of course, diamond is the most impressive one. There's a huge variety of diamonds with different colors, right? Probably the most famous one you've probably heard of is the Hope Diamond, right? That's in the Smithsonian Museum in Washington, D.C. It's this gigantic, I should have put a picture. It's just gigantic bluish diamond, and it has all these famous stories about it, like it was cursed or something like that. I think it was discovered in India, and then was brought to England, and somebody bought it. And anyway, it ended up in Washington, D.C., and it was donated to the museum. In diamond, if you put nitrogen in, it becomes kind of yellowish, kind of like these guys. And blue, if you put boron in. If you have a lot of boron impurities, it turns bluish color. So the Hope Diamond has a lot of extra boron in it. and these are not a lot of impurities. They're usually in the typically it's parts per million. So 1 out of every carbon atoms happens to be a boron or a nitrogen or something like that. Okay, so it's not a lot, but it's enough to really change its color and its value, right? So the NV center is a very special kind of one, right? So NVs are not nitrogen or boron. It's a low. You have a nitrogen, and right next to it is a vacancy, and that has its own special color and its own special properties. And its properties are very important for quantum applications, actually. So I just wanted to say a little bit more about the NV center. So I understand several of you have had are in material science, and so I hope this isn't. You probably have heard about like a, like a semiconductor model where you have a band insulator, or you have a band gap and conducting band and valence band. So a diamond is basically a semiconductor or an insulator. Yeah, it has a band gap. It's actually a really large band gap of around 5.5 electron volts. So this is, ordinary diamond. So diamond would make a great application for various electronic circuits if it weren't so difficult to work with and so expensive. It's not, silicon, on the other hand, is what we mainly are familiar with for semiconductor applications. And this is silicon bandwidth band gap is much smaller. The diamond has a really large band gap. And if you put an NV center in, you actually create localized states in the band gap. And you have these energy levels here. And they're small differences in energies on the order of electron volts, which are responsible for the colors that you see in an NV center. But what's most important is not really the color, but really what goes on down here. If you zoom in on the energy levels of this ground state of the NV center, there's actually special structure here. So this energy levels can be split, and there's 3 energy levels for the NV center. They can be split with a magnetic field, or with, actually this is strain, if you were to squeeze on the crystal somehow, or if you were to change the temperature. These energy levels are very sensitive to magnetic field, to strain, and temperature. And this sensitivity is really what's important for sensing applications. I mean, it's important for even quantum computing applications, but especially for what I want to talk about, because these NV sensors, if we can measure these kind of energy levels very precisely, we can say something about we can use them as a sensor to measure how big is the field or the strain or the temperature. Okay. So the other thing I want to point out, let's see, yeah. So the two things, the key sort of energy scales of the problem are visible light here. So the energy transitions between these energy levels, these are visible light ranges. So that's why 637 nanometers right here, that's the kind of purplish red color that you see of an NV center. And microwaves in gigahertz range. So this is we can create transitions between these energy levels with microwaves, and so that's actually very important. And so what we end up doing is we create a qubit between 2 of these energy levels here, and that's the fundamental way that NV sensors or NV centers have been used as qubits for quantum applications. So yeah. So the most important thing about the NV center is that it actually has a spin. So I don't know if you've seen this sort of spin physics before, science of spin in your quantum mechanics, in what you've had in terms of quantum mechanics, but but you know, there's the charge of the electrons that is spread out over these wave functions, but there's also the spin of those electrons, and the electron spins for NV sensor are very important. The reason is that, so you can think of the spin as basically like a little compass needle associated with that, right? So there's a spin that lives at this NV center, and it can move around in different directions. So the most important thing is we can manipulate the spin vector. We can change its direction, like from up to down, by shining microwaves on, right? So we can shine microwaves on and manipulate its energy levels and its spin. But what's really cool is that affects how bright it will fluoresce. So if the electron spin is pointing upwards, like here, then when we shine light on it, it's going to be very bright. Okay. If we reverse the spin direction and point it down and we shine light on it, it's not going to be as bright. It's kind of dark. So I don't know how clear it is in the view graph here, but the point is that, you know, this is really why the NV center is so important, and this is why, you know, many groups around the world have been studying this. And the point is that the brightness of the NV center is coupled with its spin orientation, right? So that's really key here. And that's really important because we can measure very easily how bright it is. So, you know, we shine light on it. We shine green light. You can see the little green laser here. It goes in, it hits the diamond, it radiates all those NV centers. They get excited, and then they fluoresce. They go from the excited state to the ground state, and they give off light. And the light is kind of reddish pink color at 637 nanometers. But depending on whether its spin is up or down, it will be either bright or dark. So that's really the core idea of how we can measure and manipulate these NV centers. So let me just pause and ask if anyone has any questions.
I just wanted to make a quick remark. This idea behind spin and affecting this ability for photon absorption is very similar to what you see with ion trapped systems. So when you have a kind of a calcium ion or in a kind of ion trap, I just bring it up because I think a couple weeks ago I did host a workshop on how an ion trap system works, and it's really cool seeing a similar principle of operation going on here with these color centers. I just wanted to put that out there.
Yeah, thank you. That's a very good point. One of the I mean, I don't want to sort of like say which one is better, but one of the nice things about an NV center is that it doesn't move. It's fixed in space, so we know exactly where it is. And in an ion trap, the ion can move around inside the trap, so that's a little bit of a challenge sometimes, unless you have a really good trap or something. So NV, one of the things that's really valuable about NV centers is that it's trapped there in the lattice. So if you can find it and you can shine your laser on it, you can excite a single NV center and manipulate it without having to worry about it moving somehow. There's other pros and cons of any kind of implement of a qubit, but but you're absolutely right, John. It's the same kind of principle of manipulating the spin. Now, let's see. I'm sure that you all are pretty familiar with this picture here, but let me just, for completeness, a qubit has two states, the 0 and 1 state, usually we talk about, and we can think about something called the block sphere. There's a physical reason for this, but so if you can think of like a quantum state, we can usually write it in terms of a sum of both 0 and 1, right? That's the key thing about a qubit, is that it's not classical, but it's either up or down, or in other words, it's not either 0 or 1. It can be both at the same time. And depending on what linear combination you take, the state vector, we call it, can point somewhere on the surface of the sphere, right? So if you take a pure up, if it's purely 0, it would point directly up. If you point it, if it's purely 1, it would point directly down. If you have exactly equal probabilities of both 0 and 1 at the same time, it's going to point somewhere on this equator, this dotted line here. And where on the equator it points, this phi angle, depends on the phase, the relative phase between 0 and 1. Okay, so this is a really useful analogy for NV centers, because we can talk about the spin direction is completely aligned along the direction on this block sphere. So when we change the spin direction from up to down or to somewhere in between, we're actually changing the wave vector, the state, the quantum state, right? So this is, of course, when you're dealing with quantum computing, you want to be able to change your state into different, to any arbitrary thing that you'd like. And so with an NV center, we have the tools to basically make this state point anywhere on the block sphere we'd like. Okay. And of course, there's this idea of superposition, right? So if you have a superposition of 0 and 1 at the same time, there's equal probability to measure it and see that it's either up or down, right? It's the same principle, same idea as Schrodinger's cat, where you put the cat in the box with a vial of poison, and if you don't look at it, it can really be in both states at the same time. Or if you're working for a quantum computing company, you can have a simultaneous existence of both completely done and completely not. So how do we actually manipulate it? That's this is one of the things that is really nice about NV centers, is that we know very, very well how to manipulate. We have a really good handle on how to manipulate them. So for example, if you're in the state, the 0 state, and you want to create a superposition of 0 and 1, we can actually rotate this state all the way down like this by using microwaves. And so what that means in practice is that we have a little coil near our sample, and we can pulse this coil with a voltage at microwave frequencies, and it will actually make the state rotate around. So that's a little easier said than done, but if we have the right calibrations for the power levels of the microwaves and the pulse parameters, this is very straightforward to do. And this is incidentally, this is exactly the sort of thing that people who do magnetic resonance do all the time. So like when you go to the hospital to get an MRI, the same sort of things are happening, not with any NV centers in your body, but the hydrogen in your body. The hydrogen is also a spin object. It's a really tiny, tiny magnetic moment, but it can still be manipulated in the same sorts of ways. So this is a technology that we know very well how to deal with. And so we can manipulate these spins in lots of different ways. Now, so why would we want to do this? The reason is that if we were to create, let's say that we do we prepare the state in exactly the superposition of equal probability of up and down of 0 and 1, so that the vector, the magnetization, is pointing in the plane here, right? So then we allow it to just evolve by itself. We don't do anything, we just let it sit for a while. Okay. So our what's going to happen is that the magnetization is going to actually move around. It's going to sort of move around in this plane here, and depending on the strength of any sort of interaction, like a magnetic field. Okay, so let's say that there's a magnetic field that happens. This NV center happens to be close to something magnetic. and there's a magnetic field, what's going to happen is the direction of the spin is going to start moving around the axis of the magnetic field. The same idea, it's very similar to kind of like if you I should have put a demo or something, but you know this, when you have a you've probably seen this kind of demo where someone has a bicycle wheel and they hang by one axle and it will move around. So you've seen this sort of thing. It's the same idea. So in the case of a bicycle wheel, it moves around because of the gravitational field. In an NV center, it moves around because of the magnetic field. So and what happens is you acquire this phase factor. So I'm sorry if this is too technical, but this is a, you know, when you deal with quantum mechanics, you have a state vector. You can have superposition, where in the sense that you have 0 and 1, but there's also a complex variable here. So the complex number, the amplitude, the probabilities or these coefficients can be complex numbers. And so we write the complex number here as an exponential of IBT. So this is really a complex number, but physically this BT describes a phase of this angle phi here. So in other words, as B times time, the magnetic field times time changes, we change the angle as it goes around. Okay, so over time in a fixed field, it will just move around. Okay, and so why is that so important? Well, we can measure this phase factor very precisely. There's a lot of technology that we have to measure this phase factor. Okay, and so that enables us then to have a very precise measurement of the B field, of the magnetic field. Okay, so here's a little animation of how we actually do this kind of experiment. So this is the left side shows the block sphere, and the little arrow is moving around due to our magnetic field pulses. So whenever we put on the microwave pulse, we can switch the direction of the block sphere here, of the magnetization, and then in between we let it evolve for a little bit of time. And then in the middle diagram, this shows just the XY plane, and as you can see over time, we're sort of acquiring more and more phase. So I mean, the technical word for what we're doing is we're applying unitary transformations. You may have heard about this in quantum computing applications, but this is related to doing different gate operations on a single state. And so we can measure this very precisely. In fact, there's a rather sophisticated sequence of microwave pulses and light pulses. So I won't go into the details here, but just point out that, you know, the purple and blue correspond with different pulses of microwaves. The green is our different light pulses. And then we do all kinds of sequences to measure the fluorescence. And depending on how bright the fluorescence is, we can measure how big is the phase that's been accumulated. And from that phase that's accumulated, we know something about the magnetic field. So this is sorry, it's a bit technical here, but the basic idea is that we can measure that phase that's accumulated because of the magnetic field. Okay, and this is the idea of quantum sensing. So you may have heard the term quantum sensing, and really it has to do with this principle that you create. So let me go back a page. You create a superposition between 0 and 1 of a qubit, and you let it evolve over time. And this phase factor here is something that you can measure, right? If you can measure that phase factor, that often gives you some really precise information about the system that you're studying. Okay. So here's a few examples of how this works. Okay. So I said that we can measure the brightness, and here's what happens. Like if we this is real data from our lab. we measure the brightness as we change parameters of like how long it can be in the magnetic field. So the brightness goes from positive, extra brighter, to less brighter, to more brighter and less bright. You know, it oscillates as the spin is changing its direction. So when it's up, let's see, when it's up, it's less bright. When it's down, it's more bright. So you can see that it's oscillating here, and versus time. And so we can do things like figure out how long it takes to what this oscillation period is, and that tells us the magnetic field. And then we can do some very, some sophisticated math where we take a Fourier transform and we can measure a spectrum. So ultimately, we're just measuring the brightness versus time, and that tells us about the quantum state of the system. So that would be like for a single NV center. But what's really cool is people have made a lot of progress in developing this into other kinds of sensors. So here's oh, sorry, yeah, I wanted just to say real quickly. So Tina, you had asked about the multiple quantum coherence, and so this comes to this concept. So I don't know if you've ever heard of the word Q-trit. So a Q-bit is the most common thing that people talk about on quantum computing, right? There's just two states, 0 and, oh, well, that should probably say 1, but anyway, there's just two states. A Q-trit actually has 3 states. So that's where you have, instead of 0 and 1, you have 1 extra state it could be in. And that's a little bit more complicated to deal with, because you really have to use a lot of quantum mechanics machinery to deal with it. Like by machinery, I mean theoretical concepts. You have to think about things like density matrices and Schrodinger equation a lot. And I won't go into the details, but I just want to point out that when you have a Q-bit, NV centers are Q-trits, right? So they actually have 3 states. There's 0, 1, and -1. Now, if you had a conventional qubit, you can create a superposition between 0 and 1, and you have this phase factor here. But if you have a Q-trit, you can actually do something a little bit fancier. You can make a superposition between 1 and -1 like this. Instead of doing 0 and 1, you have 0, 1, and -1. So it's sort of two extreme values of this quantum states. And when you do that, it's actually the phase factor gets another factor of 2. So that tells you that in fact, it's twice as sensitive. So if you have multiple quantum coherence of an NV center, you actually have twice as more sensitivity than you have single coherence. And so this is something that we are working on in my lab to try to implement this kind of approach here. And several people have demonstrated some beautiful experiments using second order coherence. And so when you talk about quantum coherence, you generally talk about a state of a superposition between adjacent energy levels. But if you talk about a higher order quantum coherence, that's one where you have more distant energy levels that are the superposition. Okay. But the reason for doing that is that there's several advantages to doing that. It does take a little bit more sophisticated equipment to do that, but that's possible to do. Okay, so enough of the math stuff. What is this good for? So one of the really cool things that people have done is they've developed a scanning tip here with an NV center in it. So this is a commercial company. There's a couple of different commercial companies that can do this now, but they're able to manufacture and create a tip of diamond with a little bitty pillar at the end, and there's a single NV center in the middle of that pillar. So the idea is that you have this diamond tip here and NV center in there. And because this NV center is atomic scale, it's the scale of just a nanometer in diameter or something. it really is a very, very sensitive measure of magnetic fields. Okay, so inside this diamond tip, there's this NV center. Then you've got a bunch of structure here with scanning probe head, which you can move around over the substrate or something like that. So over here, there's this magnetic sample surface, and maybe the surface has something magnetic on it, and you can image the magnetic fields that come out. So you get this beautiful sort of thing where you can do magnetic imaging over nanoscales, right? So there's a 100 nanometer bar here. This is an image of a magnetic recording material, you know, like the for data storage, right? Like your hard drive maybe. And you can see the magnetic field is changing on a length scale of less than 100 nanometers. And so you can actually image this now very precisely with one of these scanning NV center machines. And you can actually, this has been commercialized over I would say in the last 2 to 3 years, it's been commercialized. You can buy this now. It's quite powerful. And ultimately what it's doing, it's depending on this very high sensitivity of this NV center to magnetic fields. So you can measure the properties of the NV center very precisely, and then work backwards and figure out what's the magnetic field strength. So that's I think really, really powerful thing to do. People have done this now actually in biological materials. So this is like a bacterium where they put some magnetic nanoparticles inside of it, and then they could image the magnetic field using NV scanning NV sensors. So there's a way now you can sort of you can imagine attaching some sort of drugs or something to the magnetic nanoparticle and seeing how that interacts in a medical sense. And really, this is nanometer size. You can see inside of a cell, or the single cell organism. So I think this is just really exciting because I don't think anyone's really ever explored too much in terms of magnetic behavior of cells, right? From in sort of medical science, in life sciences. And a few years ago, I was trying to get money to collaborate with some people at UC Davis to really explore this in more detail. And I think this is going to grow. This is a technology that's going to become very important in the future. So personally, what I'm very interested in is applications of NV centers for detecting small. Basically, it's doing magnetic resonance at very small volumes. So what you can do is, let's say you have an NV center that is in a piece of diamond, and on top of the diamond, you put like a little drop of material that you want to study with. So for example, this could be a tiny drop of I don't know, a radioactive material or some sort of organic crystal or material that you grew, and you want to analyze it, and you'd like to understand what is the magnetic resonance of this, to do NMR, in other words. And you can apply a very complicated sequence of pulses and manipulate the NV center here to detect the tiny magnetic field created by these nuclei. So this thing on top is to be some sort of like some sort of a protein molecule, and you could do magnetic resonance of the protein molecule, and then you can get really high resolution NMR spectra. So this is very important for chemistry analysis. And so this is an example that someone did from Harvard. They did this beautiful research on this tiny droplet. I mean, this is like it's smaller than you could actually observe, this really tiny droplet. So you can get a really high resolution analysis of small volumes using this NV sensor. And this is really the promise of this quantum sensing using the NV sensor. And here's another really cool example where, if you've had, so I think someone was saying that some of you have had the 9 series, physics 9 series. So you know about the Biot-Savart law, right? So if you have a current flow, there's going to be a magnetic field that's created by it. And so what these people did was, sorry, there's a lot of information on this figure here, but this, you can see here, this kind of gray area, this is a sheet of graphene. So, you probably, I don't know if you know what graphene is. It's a single sheet of graphite, right? It's a 1 atomic layer thick of carbons bonded in a hexagonal pattern. That's what graphene is. And there's a lot of excitement about graphene as a potential material of interest for lots of applications. And one of the really interesting things about graphene is that it had the electrons, they do not travel like in a normal sense. They travel very much like light particles. So that's why people are excited about graphene. But anyway, you can move those electrons around in graphene with the same way you can move electrons in a conductor by putting an electric field on, and they can move. We create a current, and that current flow will create its own magnetic field due to Biot-Savart law, right? The flowing current creates a magnetic field, and that magnetic field can then be imaged by the NV centers, and that's exactly what's done here. So the magnetic field here was measured with an NV center by scanning over this sheet of graphene. They can measure the magnetic field. They can measure the field components along X, Y, and Z directions, right? So that's one thing I didn't say before, but the NV center is sensitive to magnetic field along all 3 directions. So it's really we call it a vector magnetometry. So it measures all 3 directions. If you know all 3 directions, you can actually back out what is the current density, what's the current flow going to look like. And so they can image the current flow in the graphene sheet. And so that's why they get these beautiful pictures here. And one of the really curious things is kind of how the flow pattern of the electrons it turns out, is very similar to like flow of like a fluid. And so you may know that in conventional metals, when you talk about electron flow, we talk about ballistic flow. Flow in graphene is something that's a little bit different, and it's partly due to the graphene having this different kind of electronic structure. But anyway, that's more of a physics nerd sort of thing, so you don't need to know about that. But the point is, the NV centers are really powerful tools for imaging these kinds of magnetic fields. I think I'm almost done. I just wanted to say one more thing here. NV centers are also really powerful for something called inertial navigation systems. So, you may know about that gyroscopes, the simple toy where you get something spinning, or even the bicycle wheel spinning, that can help you determine what direction is what in when you're flying an airplane or in a spacecraft or something like that. And so this is called inertial navigation. And it turns out that NV centers are very powerful ways for doing navigation as well. They're basically like little gyroscopes, except that they're really they spin much faster, I guess I would say. So what people have done is they in fact do the really kind of cool experiment where they create an entanglement between the electron spin of the NV with a nearby nuclear spin, and this entangled state, very much like it's an entangled spin state where you have coupling between the nuclear spin and the NV spin, and if the system were to rotate for whatever reason, you can measure that accumulated phase very precisely. And so this is something that, for example, the military is very excited about. Okay, so yeah, all right. I was just gonna, I'll just say one more thing here. My own group, we're working to develop NV centers at for detecting things at really high pressures. So this is something called the diamond anvil cell on the left here. This is used to achieve really high pressures. You can squeeze on materials and change their properties at high pressures. And you can also measure the magnetic properties with an NV center. And so this is a picture right in here. I see, I think I have, yeah. So right here is a little chip of diamond that is at the very tip of another diamond anvil, which is like, here's a picture of a diamond anvil, and it presses down, and in the very center of this is a tiny piece of diamond, and this gold strip here is our microwave antenna, and we can measure properties of materials at high pressures using the NV centers. So that's kind of where my research is focused right now. I'm sure Miranda can tell you more about this. This is from the Rodolowski group in electroengineering. She's also working with color centers, but not just NV centers. She's working with other kinds, some silicon carbide color centers, and also fabricating. You know, for example, I was talking about these little tips that you can move around, and so this is another area of research at UC Davis. So that's pretty much all I had. Here's just a picture of my research group. Probably Miranda, you know Victoria, and so that's all I have. Does anybody have any questions or comments or anything?
Oh, thank you so much for all this wonderful information and the presentation on the sort of NV centers. It's another means of quantum sensing. In fact, I wanted to ask, I did have a question. I'm certain maybe the term, the idea of a Rydberg atom, I also hear has applications for sensing as well, although through a different mechanism where we apparently seem to coax an atom's electron to be incredibly distant from the actual nucleus. And I know there's some analytically, it's a little nicer to work with as well, because if you try and do the Schrodinger equation for a helium atom or any multi-electron atom, things get very hairy because of your repulsion terms and whatnot. So I was curious, compared to Rydberg atom versus this technology, if there are any interesting distinctions between the two, or if they're sort of on a very similar vein.
Yeah, it's a great question, and you're right. So in some sense, a Rydberg atom is analogous to an NV center. It's just that it's I mean, that you can create you can use that as a qubit where you've got you can control the energy splitting very well, and then and create transitions and superpositions and that sort of thing. But the advantage, so one thing I didn't talk about was decoherence. So that's, you may have heard about this in the context of quantum computing, that decoherence is a big issue. If you create a superposition between 0 and 1, it won't stay that way forever. It will decay away fairly quickly. And of course, if you're trying to do some sort of quantum computing calculation, that's disastrous. You don't want to lose your quantum coherence. And every qubit has this because it's coupling to an environment. So they're different. Every qubit implementation, physical implementation, has pros and cons. And for many systems, like for example, the thing that like Google or D-Wave, one of these famous companies, or IBM, they talk about the quantum computers. Those are built out of Josephson junctions, and those tend to actually be pretty sensitive to the environment. The decoherence times are very fast, so that's a real disadvantage. One advantage of those Josephson junction things is that they're easy to control and create and entangle them. But on the other hand, there has this big disadvantage in terms of decoherence. NV centers and ion trap and Rydberg atoms, they have a much less problem with decoherence because they're more or less isolated. They're more isolated from the environment. Okay. And that's one of the real advantages of the Rydberg atom is that it's very decoupled from its environment. It can be really well isolated. I would say much better than an NV center. An NV center is embedded in this lattice of carbon atoms of the diamond crystal, and that's not that can be a little bit noisy. So there's a lot of algorithms to try to filter out that noise and keep it from undergoing this decoherence. And that's a big area of research in quantum technologies as to how to deal with this decoherence. Now, the Rydberg atom is even, it's much less coupled to an environment than the NV center, so it can have a much longer coherence time. But on the other hand, it moves. It can, you don't have it fixed in those. You can't pin it down so well as you can in NV center. So that makes that's a challenge. So again, there's pros and cons to every kind of qubit implementation, and it kind of depends on what application you want to work with. So that's a great question, though.
Just building on that, I wanted to ask about. I know, like there was the move from John Martinez to work at silicon quantum computing technologies now too. So I was just wondering, like, how you would compare diamond versus silicon for NV center or quantum technologies in general in terms of sensing.
Yeah, well, let's see. So I'm not sure what the silicon application you're talking about is. Is this like something like a phosphorus impurity or something? Do you know?
I do not. I'm just looking at it right now, actually.
Yeah. Well, okay. I mean, one thing that's actually quite interesting is silicon. So silicon carbide. So NV centers are in diamond are probably the most well-studied color center, but they're only one of many. And one disadvantage of NV centers is that their wavelength, the 637 nanometers, is actually pretty short. And that means that if you were to have a photon that is emitted, it will not travel too far in an optical fiber before you lose its coherence. And that's a problem if you want to entangle color centers. I didn't show this, but there was a group in Delft in the Netherlands that did an experiment where they had two diamond crystals that were in different buildings across campus. So they're more than a kilometer apart. And there was an optical fiber between these two buildings. And so they were actually able to entangle the NV spin on one building with the NV spin in another building. It's a beautiful experiment. And they were able to do, tests of like Bell's equalities. They could potentially use you could build a quantum computer this way. But the problem is that you couldn't go more than about a kilometer and still have it work because the wavelength just doesn't work well with optical fibers. This is called like telecon cutoff or something like that. So a lot of people have tried to work with other kinds of color centers that have wavelengths that are more useful, more amenable. And so a real possibility is silicon carbide. So for example, there's silicon-vacancy is another kind of color center, and there's a whole family of color centers, and silicon carbide has a lot of advantages that diamond doesn't. And so that's where Professor Radulowski's work is really focused on. So yeah, I mean, I didn't talk much at all really about quantum computing applications of NV centers, but that is a big area of research, and people have really made a lot of advances in sort of not only entangling NV centers, but also working with something, these nuclear spins. I really didn't say much about it except at the very end, but the NV center can couple to nuclear spins in its vicinity, which can be used as quantum memory. So there's a lot of really exciting ideas in terms of something called quantum internet and quantum repeaters and that sort of thing. So this is something that your generation will really hopefully take advantage of and be able to really make big advances.
The pulses you mentioned to sort of manipulate the state of this NV center, I assume they're also Rabi pulses, the same that you might see in other systems, sort of two-level systems. I mean, this is obviously a three-level system, but I see it in both ion trap systems and silicon superconducting qubits as well.
That's right. Yeah. So a Rabi oscillation is this picture here that I showed is in fact a Rabi oscillation. So this is where we turn on a microwave pulse and we can drive the system, we drive oscillations. So what you're seeing here are in fact Rabi oscillations of our system as it goes from up to down to up to down and up to down while we turn on this pulse. And so this is something that is a generic quantum phenomenon when you turn on this kind of a unit. This is called like a unitary transformation, where you use microwave or some sort of pulses to manipulate the quantum state. So that's exactly what this is showing here. This is Rabi oscillations. So one of the standard things we always do is we can measure the frequency of these Rabi oscillations, and it helps us calibrate our pulses so that we can precisely rotate the spin to anywhere we want on the Bloch sphere. So yeah, that's a key element.
And then just going off of that same slide, did you consciously decide to use fast Fourier transform? And if so, why fast Fourier transform instead of just traditional Fourier transform or other mathematical tools like Stockwell transform?
We know, okay. We use Fourier transforms all the time in magnetic resonance. It's just super easy to deal with because, with a click of a button, we can analyze a spectrum like that. And so this kind of process where we measure something in the time domain, and then we want to see the frequency content. That's very common thing to do. And we use FFT, I guess, because we're just running on the computer. I'm actually skipping a little bit of subtleties here. We actually can do something called quadrature detection. So we measure both basically a real and an imaginary component. So we can do a complex Fourier transform to get this. But that's probably a little bit more information than you need to know. But there's no reason we couldn't analyze it in some other way. It's just that Fourier transform is usually it's something we're very, very much used to. So it's very for the reason really is because when we let it. So let me see, which slide is it? I think it was right. So like in this slide here, we let this thing evolve on its own. Over time, let's say the B field is constant. Over time, this phase factor is just going to oscillate, right? This factor is cosine BT plus I sine BT. So that's a very natural, to really measure B, we just take the Fourier transform. So if we can measure it over time, we can do that, and that's exactly what's done. That's exactly what's going on. Oops, sorry, in this figure here. So this resonance frequency is telling us roughly what is the B field that we have. So yeah, I mean we're very happy that there's a lot of algorithms out there to do it. I mean the fast FFT algorithm is very efficient and works really well. Well, thanks very much for having me, guys. I would definitely encourage you to bite the bullet and take the physics quantum class, physics 115A and 115B. I've taught it for several years. I won't actually be teaching it this next quarter, but it will really give you a really strong background for quantum computing. And I hope you all go on to grad school and join the quantum workforce. So,
Thank you